Every year, it seems like students have a difficult time with circular motion. And really, when it comes to circular motion, it's no different than using the kinematic equations that we've already used in class. So as an intro, we're going to go over a few things here, and ultimately we're going to get to the kinematic equations for circular motion. So first off, it's a wonderful circle. We know that this is 0 degrees, and if we go around one complete time, that would be also 360 degrees, like that. All right, every year we do circular motion, it seems like students have a difficult time. Now, the only thing we're doing is changing some of the variables, the way they look as far as our kinematic variables. Every year, it seems like students have a difficult time with circular motion. And really, once we get into it, you'll see that it's really no different than using the three big kinematic equations that we've used before. They just end up looking a little bit different. And so to start out, we're going to talk a little bit about some of the units and variables associated with circular motion. Okay? And we have to get this idea of radians and degrees. Now, most of the time we're going to be using radians. So let's go over how to solve for radians. Now, this is not a math class, so we're not going to focus on the unit circle or anything like that. But we do need to focus on how do we go from degrees to radians. And so we know that directly to the right of a circle is 0 degrees. And if we were to go counterclockwise all the way around once, it would be 360 degrees. And from your math class, we know that's 2 pi. Right? So one complete circle around one complete time around a circle is 2 pi radians, and that's 1 revolution. Right. That means that if we go around just halfway, that would be pi. And so we know that pi is equal to 180 degrees. Now, some of you might be concerned that we'll start talking about 3 halves pi and all that other stuff. This is it, okay? And so let's say I were to be given a problem like 100 degrees, we'll make that 3 significant figures, is equal to how many radians? Okay. Now this idea of a radian, what is a radian? Well, it's really a ratio of 2 lengths. And let's not worry about the 2 lengths. But when you think about a ratio of something like meters over meters, well, those would cancel out and you really wouldn't have a unit. I look at the radian as sort of a placement for a unit versus an actual unit itself. Right? So we normally don't write 2 pi radians, but this is what we're referencing right here. Right? So if I need to go from degrees to radians, we're going to do a typical conversion. So 100 degrees over 1. And now we need some kind of conversion factor. Okay, you could use 2 pi is equal to 360, but let's just use pi equals 180. All right, you get the same answer, obviously. So we have 180 degrees is pi. And when we solve that, you'll find that we get 1.74, 1.75 radians. So some people might think, well, 100 over 180 is 5 over 9. And so isn't it 5/9 pi? Yes, that's true. But if we put in 3.14 for pi, this is what we get for radians. So does this answer make sense? Well, if you think about it, one complete time around a circle is 2 pi, and that is equal to 6.28 radians. Right? So that means 180 degrees, or pi, is equal to 3.14 radians. Okay. So is 100 degrees less than 180? Yes. Is 1.75 radians less than 3.14? Yes. So at least we know that the answer makes sense. Regardless if it's right or wrong, it at least makes sense that it should be in the proper location. Okay, but this is the right answer. So that's a quick kind of review on how you could convert from degrees to radians. Okay, so what's next? Well, how does this relate to anything that we've talked about? All right. Well, let's assume that we have an object. It's a mass, and we'll call it M for mass, right? And we're going to assume that we're swinging it in this direction. So you're holding it, you could be swinging it over your head, you could be going like this and swinging it around in a big circle. And let's assume that at some point it's located here. All right, so there's some important parts here. For one, we have a radius. Two, I already said it, we have a mass. And three, we have this angle, okay, through which the object is rotating. Now, if you think about driving in a car and you're going around the bend, you know, you're in a race, in a car race, and you're going around the bend, we don't see anything that has to do with angles. Okay, we don't see radians or degrees or anything like that. We look down at the speedometer, and it tells you how fast you're going. Okay, it doesn't say meters per second, but maybe kilometers per hour or miles per hour. All right, and we're going to get there. But first, we're going to focus just on this angle here and how it changes. All right. So if the object stays at a nice constant speed the whole way around, that means the angular velocity, the velocity at which the angle is changing, would be constant. If it's speeding up, then that angle should be changing at a different rate as we move around there. Okay? And so I'm going to write down our original kinematic equations, all right, and I'm going to write down the variables associated with each. So our three big kinematic equations were VF equals VI plus AT. Don't forget those vectors. VF squared equals VI squared plus 2AX. And X equals VIT plus 1/2 AT squared. For anybody that's watching this that has done kinematic equations and stuff, these should be very, very well known by now. Now, some of the things that you might see that are different is I tend to use an I instead of a little zero for not, but they mean the same exact thing. All right, final velocity, initial velocity, acceleration, time, and X is displacement. So if you notice here, I didn't write anything up here that has a V or an X. All right, so let's go back here and let's write down the variable and the unit. There's four possible variables, okay, from our kinematic equations. You have X, you have a V, you have an A, and you have a T. And if you remember, the units were meters, meters per second squared, and seconds. Okay. Now I'm going to tell you right now that time does not change. We don't need to mess around with time at all. There's no other way that we're going to measure the length of the interval. It's just going to be in seconds or hours or something, okay? Most likely seconds. Now, if I were going to look at the circular motion, so that's circular motion variables. what do you think they're going to be? Okay. Well, for x, we don't have a displacement anymore as far as like a linear displacement, but we do have an angular displacement. And we're going to substitute in theta. All right, Theta, straight from your math class. For velocity, we're going to have an angular velocity, and that is omega. Hopefully you can read that. Hopefully it's not too small. And then lastly, instead of just an acceleration linearly, we have an angular acceleration that we call alpha. And so the units, instead of meters, radians. Now, this is pretty easy after that, because anywhere we see m, we're just going to substitute in radians. So radians per second, and radians per second squared. Right. So now what I want to do is I am going to take my kinematic equations, and anywhere where I see x, I'll put theta, v, omega, a, alpha. And then we're going to have our new equations for circular motion. Now, these aren't the only ones, but for now, this is the ones we are concerned about. And when you're writing these, at first, you might get a little confused because you're so used to writing the v's, and I do the same exact thing. And then lastly, theta omega it plus 1/2 alpha t squared. Okay? So here they are, the three big equations that we're going to use for now. Now you'll notice the very last thing, I put vector signs on them. Well, I don't know about you, but when I think of objects moving, I always think about them moving clockwise. And this is where I get not in trouble, and it's not like I'm really concerned about it, because as long as you're consistent, it's fine. But I tend to call this direction positive, and that's not really true. Okay? So in my head, whenever I see things moving and they're positive, I always see them moving clockwise. All right? Whenever I see them negative, I always picture them going the other way, but that's not really true. So clockwise, CW is actually, see, I just did it, is actually the negative. And when we go the other way, counterclockwise, that is going to be positive. Okay? I mean, why is that? If we think about it, we think about our circle pointing to the right, 0, 90, 180. So when you move counterclockwise, you're increasing your angle. So it makes sense if we think about it as far as math goes. So this is your basic setup for your equations, and this is where they come from. Okay? We have all of our units here. And we have here our three big equations that we need. Okay? Now, sometimes you'll hear me refer to the W as angular velocity, and other times you'll hear me just say omega, but you have to realize, right, it's the same exact thing. One's just using the Greek, the name for it. So in the next videos, we're going to get into some problems.